So gravitational fields in high level builds on the concepts that you learnt in standard level. So let's review those first. Take a step back now and think about the following questions. Write down the answers on your notes. If necessary, go back to your previous SL topic information and revise it. You need to be able to define a gravitational field. You should be able to describe the gravitational force between two masses. You need to be able to state in which direction the gravitational field acts. You should be able to define gravitational field strength, state whether it's a vector or a scalar, and explain how you would represent a field around a mass. Now these are all standard level requirements. So stop, go to the textbook or your notes and do a little bit of revision. So a good idea would be to now test what you already know, and if necessary, check with a textbook or some other resources. But define what a gravitational field is. Describe, using a relationship, what the gravitational force between two masses might be. State the direction in which the gravitational field acts. Define gravitational field strength. State if gravitational field strength is a vector or a scalar. And in a diagram, show how you would draw or represent the field around a mass. Stop the video and see if you can do these. So let's see how you did with these. A gravitational field is any area which experiences a gravitational force. So this goes back to our original definitions of a field, which is an area, a force field I should say, which is an area where there's a force, and if it's gravitational field, it's an area where you experience a gravitational force. The gravitational forces between two masses are described by Newton's law of gravitation as F equals G m over r squared, where the m's represent the two masses involved. You tend to have a large mass and a small mass, but that's not necessarily the case. This expression is also sometimes written as Gm1, m2, but it pretty much stands for the same thing, divided by the distance between them squared. Now I'll just mention something about that distance. When measuring the distance between two masses, we measure the distance from the centre. And we assume, when we're doing our calculations, that the masses, regardless of their size, are concentrated as point masses. And that's why we use the centre point. In reality, the behaviour inside the planet is very, very different to a uniformly distributed sphere. But we'll worry about that a little bit later. So for now, just to go back to this formula, Newton's law of gravitational is force G m1 m2 over r squared, and G is our gravitational constant, which is equal to 6.67 times 10 to the minus 11 meters cubed, kilograms to the minus 1, seconds to the minus 2. Now, in terms of direction, gravitational forces can only be attractive. Now, this is as opposed to electrical forces, which happen to be attractive and repulsive as well. So the peculiarity of gravitational forces is that they're only attractive. Now, gravitational field strength, by definition, is the force acting per unit mass. The relationship can be evolved using the same idea. Gravitation, Newton's law of gravitation, F equals G m r squared per unit mass. Now by unit mass, we are referring to the mass of the object in the field. So for example, if we're looking at a satellite orbiting the Earth, that would be your small m, your big M, or your M1 and M2. And your mass that you're dividing by is the mass of the object in the field. So we would divide the force by that mass, and we would end up with small g, gravitational field strength, equals g m, mass of the planet, over r squared. Now, because gravitational field strength is force over mass, force being a vector and mass being a scalar, the gravitational field strength is a vector too. Now the last thing we want to do is to represent field lines, and I'll show you that on the next slide using the idea of the field lines around a planet. So here are the field lines around a spherical mass. And there are 3 points that we need to draw attention to. The first one is the direction. The direction is the direction that the force would be acting on a point mass in the field, which is towards the planet. Secondly, how the field strength is represented. The field strength is equal to the density of the lines. Okay, now you don't need to know that in any mathematical sense, but you do need to show or demonstrate your knowledge that the closer the lines are, the stronger the field. So therefore, you have a stronger field on the Earth's surface, and as you get further away, the lines get further apart, and so demonstrating a weaker field strength. The third thing that you have to note is that the lines are perpendicular, let me draw that again, to the surface. And in fact, when we get very close to the surface, if we really zoom in, you would assume at distances or heights which are close to the Earth, you would assume that these lines are in fact parallel. So that's why when we talk about field strength G, we usually use 9.81. Unchanging. It's a constant value. We now know that it's not. It's actually equal to gm over r squared, and therefore a product of changes in the radius. But however, very close to the Earth's surface, we can assume that these lines are parallel, and so therefore the field strength is staying the same, and staying the same at a value equal to 9.81 newtons per kilogram. We will come to this a little bit later on, however. So what makes high-level fields different? Well, we're going to start off by talking about potential energy and the potential energy of objects within the field. In the past, we've always talked about GPE, or gravitational potential energy, as mgh, where m is the mass of the object, g is the acceleration of gravity, or gravitational field strength, and h is the height above the defined, chosen zero potential energy point, which usually is the floor. So we lift something up, we have that change in height, we could use it to find the potential energy gained, or simply work out the GPE by using the height it's moved to. Now, what are the problems with this definition? Well, the problem with using that relationship is that it is only valid when the acceleration due to gravity, or the gravitational field strength, is constant. As you now know, G is not constant. We've assumed that it's constant on the surface of the Earth, but in fact it's actually gm over r squared. The second thing that we have assumed is this arbitrary place where potential energy starts off being zero. Now this is fine if you are always using the floor, but when you are using interplanetary systems or further afield looking at other astronomical objects, then you can't use the surface of the floor as your 0 point. So the problem with this equation is that our 0 potential energy point is variable, and we can't have that. So the three relationships that we're going to define now are potential energy, potential, and potential difference. And the links between them are very logical. So although you will be given the three relationships in the data booklet, it's very, very common that you be asked how to derive them. So let's have a look at those relationships. So, super dense definition coming up, and yes, you do need to learn it off by heart. The total gravitational potential energy of a system is defined as the work done in bringing all the masses of the system to their present position, assuming that they were originally at infinity. So this is our premise. When you have an object which you have raised above the floor to put it at point X, you have done some work, and that work is equal to your GPE. Now, if you were to take that object X to infinity, it would end up having 0 energy. Why? Because infinity is chosen to be the place where gravitational and electric potential energies are equal to 0. Right, so basically what this means is that the potential energy that you give, the GP that you give it, plus the work done in taking it to infinity would be equal to 0. Because that's the potential energy that it would have in infinity. And in fact, another thing is also true, that the amount of energy to bring the object to point X is also equal to the gravitational potential that it has. This is completely insane and very difficult to understand, but luckily it's not something that's particularly necessary for any numerical questions. And in terms of definitions, well, you just have to learn those. So that was a little bit abstract, but there's no reason why the derivation should be. Let's say we have an object at position X, a distance of r from the centre of the Earth. Remember, we assume a point mass. Now, to get the object there, you must do work against the field. So, work equals force times distance. Now, what is the force? G m over r squared. And what is the distance that we have moved it? That's times r. Now that work is equal to the potential energy because it's work done against the field and equivalent energy given to the object in the field now. Now these r's cancel out and we end up with this relationship. In addition, we need to add a minus sign. So let me explain why there's a minus sign. Now, as already stated, infinity is a position chosen because that is the place where the potential energy is equal to 0. So now think of an object which is on the surface of the Earth. As it moves up, let's say you're throwing a ball, imagine that you could throw a ball up into infinity, as if that was ever going to happen. But anyway, imagine that you are raising a ball. You would start off with maximum kinetic energy and minimum gravitational potential. Okay. Now that potential energy must increase with height as it loses kinetic energy and gains potential energy. However, as it increases and moves towards the infinity point, it must be increasing up into a maximum of 0. Now, the only way that you can increase the amount of potential energy up to a maximum of 0 is if we start with the largest negative value. So therefore, we use a minus sign to denote this. So now try this question. Work out the gravitational energy needed to bring a 1 kilogram mass to the surface of the Earth from infinity. What information do you need? So first you will need the radius of the Earth, 6,371 kilometers, and the mass of the Earth, which is 5.97 times 10 to the 24 kilograms. This information will always be given to you in the exam. What relationship are we using? Now we're using the gravitational energy needed to bring a 1 kilogram mass. So we would apply EP equals G M over R. And that should give you your value of minus 62.5. So now we're going to define a quantity called gravitational potential. Now the gravitational potential is defined as the work done per unit mass in bringing a small test mass from infinity to that position. So pretty much what we're dealing with is potential energy, because that's what potential energy was. The work done bringing an object from infinity to some point x. Now what is different about this is that it's the potential energy over the mass of the object. The work done, remember, and the potential energy are equivalent to each other. So I'm referring to potential energy because that's the expression we have just been working with. So now all we have to do is divide potential energy by the mass of the object. And that gives us an expression for potential, which is potential energy per unit mass. Potential is given symbols of Vg and has the units of joules per kilogram. I'm not referring to electric field issues just now. I'll come to those later. And we're just going to stick to the gravitational field theory. It's important also to remember that potential is a scalar quantity. Now stop the video and try and derive an expression for potential in terms of the mass of the planet. Okay, so potential in terms of the mass of the planet and the position of the object in the field. Okay, so that's simple enough. We have the potential energy, which is G M over R, but it's per unit mass. So of course these two cancel out and we end up with G M over R. Okay, and that's how we work out potential. Now let's have a look at this question. It's super straightforward. You're given the potential, the gravitational potential Vg on the surface of a planet as equal to 4.8 minus megajoules. I should of course have said minus 4.8 megajoules. Okay, and you need to work out the potential energy of a mass of 86 kilograms. Well, remember, potential is the energy per unit mass. So therefore, the potential energy would be 4.8 times 86 kilograms. which should give you this value. So this is another good question. So here we have an object on the surface and the gravitational potential at a height of 500 kilometers above the Earth is now minus 58 megajoules. So how much energy or potential energy must be transferred to the mass to raise it to this point? So how much energy do you need to give it? What is the difference in energy between this point here and this point here? Now, in order to do this, you must work out the potential here. That's the amount of energy per unit mass. If you know that, you can work out the difference between the two to see how much energy you need to give an object here to get it up here. Now you should remember the value that we got in the previous question, which was minus 62.5 megajoules. So work out the difference between the two from here to here, and that will give you the amount of energy per unit mass that you will need to bring the object up to here. And once you know that, then you multiply it by the mass of the object to give you the total energy. Because remember, this is potential, and potential is energy per unit mass. What you've actually worked out in the previous question is the difference between the potential of two places. So you've worked out something called the potential difference. And yes, you have come across it before when we're doing current electricity. Now, the potential difference between 2 points is the work done in moving a unit mass between 2 points. Our relationship for potential difference is the same, but it's the work done moving an object between those 2 points. Not from infinity, but between point A and B. And that will give you the potential difference between objects A and B. Let's try another question that's like this. So what is the gravitational potential difference between the top and bottom of a 24.5 meter tall building? Now for this question, I'm going to give you some hints. Once again, and I'm going to exaggerate this diagram, what we are dealing with is a position 1, which is the surface of the Earth. So if you need to find out what the potential is on the surface of the Earth. And then you need to find the potential at this new position, which will now be R plus 24.5. Now you'll be saying, hang on a second, we've already worked this out. We got 62 point something. Now you have to do it again because the significant figures that you were using are such that by adding 24.5 meters to the radius of the Earth, which is a humongous amount, then you won't register a difference in your potential. So what you have to do is go back and work out a value for the potential on the surface of the Earth to a much, much higher degree of precision. Do not round it up. Then work out the potential up here and then subtract the values. And you should get 240 joules per kilogram. Equipotentials. A field line, which we've come across before, represents the direction of force on a mass. If the field lines get closer together, it means the field strength is increasing. So the field lines represent which way the force is acting on an object. It will tell you which way it's going to go if the force is acting. So what are equipotentials? Equipotentials are points in the field which have the same potential. And remember, potential is the amount of energy, potential energy, that an object has per unit mass. So it's points along a field that would require the same amount of energy to get to. Now, equipotentials have rules, and they're very easy to draw if you follow those rules. Now, gravitational field lines are always, always, always perpendicular to equipotential surfaces. That's the first thing. So when you're drawing these equipotentials, usually what happens is the field lines are there already. So you have to make sure that the equipotential points not only are marking places of equal potential, but that when you draw the field lines, the equipotential, you make sure that there are 90 degrees to the field lines. So that's the first point, the perpendicular aspect to it. The second one is they always point from high potential to low potential. So in this case, the field lines are going towards the floor, which is at a lower potential. Now that's when that minus thing can get really confusing, but remember, potential is a scalar. So by lower potential, we mean magnitude, lower potential in magnitude. Here are some examples of some equipotential lines, and they're quite interesting when the field lines are not present. The field lines would be radial in that sense. And as you can see, they show that the field strength is much stronger because even the equipotentials are closer together.